It's forces this week. So what goes up must come down. One of Newton's theories of motion. I really hope you enjoy your lessons on forces this week. I'm just going to go back and see if I can juggle these. So one of the forces that you're going to look at is magnetism, and the Earth has a magnetic field around it which stops it from being burnt to a crust by the sun. We're really lucky that we live on this planet. But you might remember about the poles, the North Pole and the South Pole, and we did some work with magnets and iron filings, and you saw how the iron filings made a shape coming out from the north and the south, showing the magnetic field, and it really is quite magical, that. So with gravity, so say we had we've just had Elon Musk. He's doing like private trips into space, and so he's here, Cape Canaveral, so it's around about here. And so say he had 2 rockets going to space for a trip. If the 2 rockets take off, the gravitational force between the rockets isn't much. Okay, it's not, gravity isn't. It's a weak force, but because of the gravitational pull of the Earth, the gravity between the rocket and the Earth is really big. So the 2 rockets, they would experience a really big gravitational pull towards the Earth, but actually between them there's not much. And also with the ISS, I've been watching that actually over the last couple of nights because it's been going over. It's not true that there's no gravity. There's sort of microgravity up there, but yeah, very useful for running around this park and juggling gravity. It's coming very useful this morning. Now, gravity attracts all objects towards one another, and everything in the universe, including this book, has a gravitational pull that is trying to draw other objects towards it. And the gravity made, by the Earth is what keeps our feet firmly on the ground. Without gravity, we would be floating off into the air. Now, the size of something isn't important. It's the mass that determines its gravitational pull, and it's trying to attract objects to it. So if it's got more mass, it's going to have a bigger gravitational pull. Now Earth, okay, now this isn't to scale, my solar system is not to scale. Earth is 4 times smaller than Uranus, but Earth and Uranus have the same mass. They have the same gravitational pull, even though Uranus is 4 times larger. So as you can see, I'm being very brave this morning because I'm very near some birds. Everyone knows how frightened I am of birds. I was the one hiding in the cupboard when the bird expert came. And so everything that flies uses air resistance, so birds and aeroplanes. And that is all connected with air pressure. And air pressure is to do with how much air you can get in a patch, the pressure of air in one patch, okay? And the denser it is, the more air pressure it has. Now, when you're measuring forces, you need to use a bit of equipment, okay? And you might come across these when you're in year 5 and 6, but I just thought I'd introduce them to you because these are called a Newton meter. And you might remember Sir Isaac Newton. We made the wig, we did about his experiments into light, and you're going to learn about his laws of motion this week as well. Now, this Newton meter that measures forces, it measures mass as well. You can do weight as well, but we don't really use it for that. Hanging it up like that and then hanging something on it, it's not really for that, okay? It's more to measure the energy, okay, when a force is applied. Okay, so what I'm going to do, I'm going to show you, you calibrate it using this screw at the top, and it's got the scale for the Newton, got 1 Newton, 2 Newtons, 3, 4, 5, and it's got a spring in it as well. And you calibrate it so that that green bit there is just on the 0. And if you want to kind of measure how many newtons are in the work or the torque, that kind of thing, you clip it on like that, and normally you'd have a partner looking at this scale, and then you drag it and you see what force is being exerted when it's dragged. And sometimes you have to do a bit of estimating and a bit of averaging out. But I just thought I'd show you that because that's how you measure forces. Okay, quick recap on friction. Friction is essential for us to move around. It's a fabulous force. And we would be sliding all over the place if we didn't have friction. And everything, the way friction works is everything is covered in microscopic bumps and lumps. And even this beautiful shiny bit on my bike, that has got microscopic bumps and lumps all over it. And the amount of friction something's got is how easier it is for two surfaces to slide over each other. Now, you can see on this, my tyre is really nice and bumpy, okay? And also, the ground is asphalt, and it's nice and bumpy. And that means we've got lots of friction going on there because the surfaces are going to be harder, so you're going to get more stability, okay? Ice skating. So ice skating, you've got the blades and you've got the ice. They've still got microscopic particles of lumps and bumps, but they're smoother, so you can glide more easily over them. And not so much about harder, actually. It's more about materials with friction. So my shoelace here, this is all friction, okay? Everything is about friction. I wouldn't be able to tie my shoelace unless there was friction at work. If you put your hands together, if you press, it's really hard for you to then move. Yeah? But if you just press lightly, you can do it really easily. And that's the power of friction. So I've just got a bit of a better demonstration here about work and energy, okay, and measuring forces. And so I've got an elastic band here. This is a good demonstration of tension, actually. When the elastic band is like that, that's kind of equilibrium. And then when I pull it, you might remember pushes and pulls and things like that, those are now balanced, okay? And I think you're going to watch a little video about Newton and his laws of motion. That's now a balanced force. And when I let it go, oh, that's equilibrium again. Right, I'm just going to show you on this because this is a better example. And so I'm going to pull. I've calibrated already. I'm going to pull, and you can see, oh, that's 1 Newton. That's 1.5 newtons, because you're doing decimals this week. 2, that's 2. Well, that's interesting. You know what, I should have got a ruler out as well. 2, let's do 2.5. Or shall I see how far I can go? Right, that's 2.5. 3 newtons. Shall I keep going? Oh, better not let this go. All this energy. Right, that is 3.5. That's 4 newtons. I hope this elastic band isn't going to break because I'm really going to get sore wrists if it does. And 4.5 newtons. Ah! So 4.5 is the limit. Oh, that was fun. So gravity pulls everything down at the same speed. But you might have noticed that some objects, they fall more slowly than others. And that is because of the air, because the air is made up of gases. And thinking about air resistance and water resistance, you can see that if you try and move something really quickly through water, it's quite difficult. If I put my hand in the pond, and I move it really quickly through water, it's quite difficult. And it's a similar thing with air resistance. So I think in the lesson I talk about invisibility, and there's another fantastic force here, magnets, magnetism, and it can be quite invisible actually. So we've got our Earth, and you might remember when we did forces before, we did magnetism, we did about the poles, and we did about the north and the south. We did a little bit about northern lights, solar winds and all that, how that works. And you had bar magnets in school, and you knew that a north and a north, they repel, and a south and a south, they repel, yeah? But a north and a south, they're friends, okay? Really good. And you investigated lots of different magnets. I've got a few here. There's sort of some circular ones, some horseshoe magnets, but they've all got like north and south. And we also found out that there are certain metals that are magnetic. Not all metals are. And it was iron, nickel and cobalt. I think you might remember that. And I'm just going to see if my slinky is magnetic. Oh! It is. So everything that flies through the air uses air resistance, and you might remember Captain Tom. We did a little fly past with our paper aeroplanes for Captain Tom on VE Day. So we can go back and have a little think about our paper aeroplanes. Now, paper aeroplanes, any aeroplane actually, not just paper ones, they use air pressure in order to take off. And when an aeroplane moves forward, air passes, it passes over and it passes under its wings, and that's due to the shape of an aeroplane's wings, and the air is all squeezed together when it moves under the wing, and the high pressure pushes up, okay, against the wings of the aeroplane as it tries to expand the low pressure, and the force of the high pressure of the air is what pushes the aeroplanes off the ground.